Try to think of something you can do without using energy. We need energy for everything we do in our day-to-day lives, even though it's not something we think much about. Energy is the ability to do work. What's work? We'll get to that later. Most types of energy can be classified as kinetic or potential energy, so let's explore what each variation really is. Remember, energy can shift between forms, but it is never created nor destroyed. This is key to understanding how energy behaves in the real world. Kinetic energy is the energy of movement. It can be calculated by Ke equals 1/2 mass times velocity squared. Say someone is throwing a ball that has a mass of 3 kilograms. It's traveling at 5 meters per second. After a few calculations, we can determine that Ke equals 37.5 joules. But what if we wanted the ball to travel at 10 meters per second, not 5? The mass is going to stay the same, so the only thing we can do is increase the kinetic energy used. Reworking the equation, we now need to use 150 joules to go twice as fast. There's also another kind of kinetic energy, rotational energy, which is proportional to how many times the ball spins as well as the ball's size, shape, and mass. Thermal energy is energy with a direct relation to temperature. While we can't necessarily see the vibrations of atoms, we can feel that through temperature. If there's a difference between the temperature of an environment and a system within it, then heat or thermal energy is transferred between them. For example, this cup of hot chocolate is losing heat energy as it cools to room temperature. It's also important to know that the temperature of the room is also increasing. However, since it's so much larger than the cup of hot chocolate, its temperature increases very little in comparison to how much the cup of hot chocolate's temperature decreases. Heat typically flows from an area of high temperature into an area of low temperature. Once all the parts of the system reach the same temperature, they approach a thermal equilibrium. It's also worth noting that some objects are easier to heat up than others. Heat capacity is our way of determining how much energy it takes to raise a material 1 degree in temperature. For example, a steel pot takes less energy to heat up if it is empty than if said steel pot also contains water, because water has a higher heat capacity. The energy of sound is made when things vibrate. Think of the strings on a guitar. Sound is able to travel when these vibrations hit other objects, causing them to vibrate too. It can travel through liquid, solid, or gas, but not vacuum. Sound also travels in waves. These have different frequencies and wavelengths, which determine the pitch and how loud the sound is. Another type of energy, separate from kinetic energy, but not quite potential, is called radiant or electromagnetic energy. Electromagnetic energy is essentially the same as light. It can take the form of visible light, like candles or light bulbs, or invisible waves, like radio waves, microwaves, X-rays, and gamma rays. Unlike sound, this type of radiation can travel in a vacuum. It is also made up of tiny particles called photons, which travel at the speed of light. In nature, electromagnetic energy can be transferred into chemical energy through photosynthesis. And that brings us to our next type of energy, potential energy. Potential energy is any type of energy that is stored, of which there are 4 types: gravitational, chemical, nuclear, and elastic. As a mass moves farther away from the center of a planet or other object with high gravity, gravitational potential energy increases. Say we have an elephant and lift it about, say, 10 feet off the ground. Lifting this elephant is called work, or when energy is transferred from one system to another. In this case, this would mean when energy is transferred from whatever is lifting the elephant to the elephant. Naturally, it takes more and more work to lift the elephant higher. As it's lifted higher, more and more gravitational energy is stored. Let's take another elephant and lift it 20 feet off the ground. The elephant that is higher up is going to have more gravitational potential energy because it's higher up and, therefore, has more work energy put into it. Now let's move on to chemical energy. Chemical energy is stored within the bonds of atoms and compounds. When bonds are formed and broken, stored energy is released. Chemical reactions that overall produce energy are exothermic. Think about burning wood. The chemical reactions taking place here release energy as heat and light. Reactions that absorb energy are endothermic, like ice melting. It absorbs energy to become warm enough to melt. Now let's move on to nuclear energy. The nuclear power plants of today are powered by a process called fission. Uranium or plutonium atoms are broken apart, which releases electromagnetic and thermal energy. Nuclear energy is stored in what is called the nucleus of an atom. Nuclear reactions change the identity of atoms by splitting up the protons in a nucleus, fission, or combining 2 nuclei together, fusion. Elastic energy can be stored in a compressed gas or liquid, in something like a spring, or in something stretched, like an elastic band. The energy can be found in the strain between the bonds in the atoms. When they are stressed, they absorb energy. When they are released, they are relaxed. Remember our definition of work? It is when energy is transferred from one system to another. Here are some examples. When we eat, our bodies transform the energy contained in food into energy we can use to do work. As we run or walk, this chemical potential energy is transformed into kinetic energy. The food chain also shows a good example of how energy is transferred from one system to another system. Energy from the sun, radiant energy, reaches the earth and is converted to stored energy inside a plant. Then, when a rabbit comes to eat the plant, the energy is converted into energy that the rabbit uses to run and jump, kinetic energy. When a fox catches the rabbit, it eats the leftover stored energy for its own kinetic motion. It may appear that energy is lost throughout the food chain. Only 10% of the energy used for plant growth is taken into the body of a carnivore. However, along the way, energy is released through motion or through undigested parts, which are released as feces. Another example can be shown by how we use coal to fuel our everyday lives. Much like a plant, considering that coal is partially decayed plant matter, it contains chemical potential energy, which can be released by forming or breaking bonds. Through combustion, this energy is released as heat and light, the energy that we use to fuel our homes. It's important to remember that energy is different from power. Energy is the ability to do work, while work is the act of exerting a force over a distance. Units used to measure energy are joules, BTUs, Newton meters, watt hours, and calories. Here's the difference between energy and power. While energy tells us how much work is done, power tells us how much energy is exerted over a unit of time. Power is essentially energy per unit of time. It's typically measured in watts. We can find power with change in energy over time. Here are some important things to remember about energy and power. Energy is the ability to do work. Work is when energy is transferred from one system to another. Power is energy per unit of time. There are two main types of energy, potential and kinetic energy. Potential energy contains gravitational, chemical, nuclear, and elastic. Kinetic energy contains motion, thermal, and sound. Radiant energy is also an important type of energy. Ke equals 1/2 mass times velocity squared. Energy can shift between forms, but it can never be created nor destroyed.